Dear students, in today's class, let us discuss about torque acting on an electric dipole. See, if we place an electric dipole in the presence of uniform electric field. Uniform electric field means if we consider any region, the electric field at any point on that region is equal in both magnitude and direction. Then we call that region as a uniform electric field, and that uniform electric field is always represented by drawing parallel equidistant lines. So if we draw a parallel equidistant line, it means that is the representation of uniform electric field. Okay. If we place any dipole in this uniform electric field, by this electric field on this dipole, the force will act. So there are two charges in a dipole, right? So by this electric field on this charge, the force will act on individual charges. Okay. So due to that force, the torque will be formed, developed in the dipole, and due to the torque developed in the dipole, so we know significance of torque. Torque will act on a body to rotate it in the first PU itself, right? So here also by this electric field on this dipole, torque will act on it. Due to that torque, the electric dipole started to rotate. So let me discuss what is the amount of torque acting on this dipole. So when the torque acts on the dipole, so the dipole will rotate it until the dipole orients its direction along the direction of electric field. See, this is at an angle theta, right? When torque acts on this dipole, so this torque will continue to act on this dipole until this dipole orient in the direction of electric field. Okay. So now, what is the amount of torque acting on this dipole by this electric field that we have to discuss? For that, let us consider an electric dipole that is consisting of two charges, one negative and one positive charge. So that is electric dipole AB, that is placed in the presence of uniform electric field. Okay. So here, the direction of dipole moment is from negative to positive charge, and it is placed at an angle theta with the direction of electric field. Here I am just written the same thing here. Okay. So the direction of dipole moment is at an angle theta with the direction of the electric field. Now, so this dipole having a dipole length as 2a. Now, so by this electric field on this positive charge, some force will act on it. So the force acting on the positive charge due to this uniform electric field is given by magnitude of the force is F is equal to Q into E. And direction of the force is along the direction of electric field. Okay. So since the charge is positive here, so we write, so from the definition of electric field, we write it is the force per unit positive charge, or simply we consider the any charge force acting on that charge. So F is equal to QE into E. If charge is positive plus QE, that means force and electric field are acting along the same direction. So since this is the positive charge, the force is acting along the direction of electric field, and magnitude of the force is F is equal to QE into E. And in the same way, so if we consider negative charge, the force acting on the negative charge is given by F is equal to, magnitude of the force is F is equal to. So magnitude means we will consider only the strength, not the sign. So QE into E only. But the direction of the force acting on the negative charge is, since here we are considering negative charge, the direction of force is opposite to the direction of electric field. This is the direction of electric field, but the force is acting in opposite direction, right? So now see, the force acting on positive and negative charge both are equal in magnitude but opposite in direction. So force due to positive charge and force due to negative charge are same in magnitude but opposite in direction. So we say here in the dipole two equal and opposite forces are acting on a dipole at different lines of action. Different lines of action means, see, this is one line of action and this is one line of action. So if two forces, two equal and opposite forces acting at different lines of action, then that constitute a couple, means torque, right? So here also the two forces are equal in magnitude but opposite in direction and acting at the different lines of action. That's why it will constitute the torque or couple. Okay, and torque will act on it. Then what is the value of torque? How we can find out the value of torque? So by the definition of torque, we know torque is nothing but the product of force, either of the force means, so among two forces we can consider any one force, either of the force into perpendicular distance between those two forces. Perpendicular distance means, see, this is one force and this is one force. These two are the forces. The perpendicular distance between them is, see here, that is BC, right? So torque is given by tau is equal to force. Any one force value is QE. So QE into perpendicular distance is BC. Now we need to find out the value of BC. So in order to find out the value of BC, now see ABC, the right angle triangle. Consider the right angle triangle BCA. Right. So here we have considered this BCA. So here we are having, see, this dipole moment or dipole makes an angle theta with direction of electric field, right? If this is theta, this can also be written as theta by corresponding angle concept. So at the point A we are having angle theta. This is 90 degree. By using the trigonometric functions definition, now we need to find out BC value, right? Means BC is opposite side. We don't know the value of adjacent side. So we know the value of hypotenuse side, that is nothing but the dipole length, that is 2a. Okay, if we know hypotenuse, we can find the opposite side value by using trigonometry function, that is sin theta. So by AB. AB means nothing but 2a, right? So we write BC by 2a. So BC is equal to how much? Now take this 2a to this side. So we get 2a into sin theta. Now substitute the value of BC in this equation. So we get torque, that is tau is equal to QE into BC value is 2a sin theta. We know dipole moment is the product of charge and dipole. So Q into 2a can be written as the dipole moment P. So we write P into remaining is E sin theta. This is the expression for torque acting on an electric dipole that is placed in the uniform electric field. So the amount of torque acting on an electric dipole, so due to the electric field, due to the uniform electric field, is tau is equal to P sin theta. Now see, this is in the form of product of magnitude of two vectors and sine of the angle between them. That is nothing but the vector product of the two vectors. So this torque is a vector quantity and it can be written in vector form. Torque acting on a dipole can be written in vector form as vector tau is equal to vector P cross vector E. So torque can also be defined as the cross product of dipole moment vector and electric field vector. Okay, and the SI unit of this torque is Newton meter. SI unit of the torque is Newton meter. Okay, so now when does this torque acting on a dipole is maximum and minimum? Let us discuss that. When do we say the torque acting, maximum torque acts on the dipole and minimum torque acts on the dipole? Now consider the expression for magnitude of the torque, that is tau is equal to what? Pe sin theta, right? So if the dipole moment, we know theta is the angle between dipole moment and the electric field, right? If the dipole is acting along the direction of the electric field, if the dipole is acting along the direction of electric field, see, this is negative charge and this is positive charge, and the dipole moment is also acting along this direction. If the dipole moment direction and electric field vector direction are same, then angle between them is 0 degree. That means if the dipole is along the direction of field or opposite to the direction of field, that means if theta is 0 or 180 degree. See, the torque will act on the dipole to orient it along the direction of electric field, right? But already the dipole is in the direction of electric field, means it is along the direction of electric field. That's why there is no need to apply torque, right? Now see, in mathematically, so theta is 0 degree, or if it is opposite, so theta is 180 degree. Then sin 0 or sin 180 value will be equal to 0. Right. So now substitute this value in this equation. Tau is equal to Pe into 0. So 0 multiplied by anything is nothing but 0. That is torque is 0. That is minimum. That means the minimum torque will act on it. Means no torque acts on this body. No torque acts on this dipole, electric dipole, because the dipole is already in the direction of the electric field. Torque is acting on the dipole in order to orient it along the direction of electric field, but it is already oriented. That's why the torque acting on it is 0 or minimum. Then suppose if the dipole is perpendicular to the direction of electric field. If the dipole is oriented perpendicular to the direction of electric field, then what happens? See, this is the direction of electric field. Just consider this is the direction of electric field and this is the direction of the dipole moment, that is P cap, or dipole moment vector, that is P vector. So now the angle between vector E and vector P is 90 degree. That means theta is 90 degree. If theta is 90 degree, then sin 90 value is maximum, that is equal to 1, right? So if sin 90 is 1, then tau is equal to Pe, sin theta value is 1, therefore Pe into 1, that is tau is equal to Pe. That means maximum torque will act on this dipole. When the dipole is perpendicular to the direction of electric field, then maximum torque acts on the dipole, that is equal to P, in order to orient it in the direction of electric field. This is about the torque acting on a dipole. Okay. So then, in the case of an electric dipole, the net force acting on the dipole is always equal to 0, because see, this is vector F minus QE vector and this is plus QE vector. So when we consider net force, total force value is added, vector sum. So they get cancelled. So net force acting on a dipole due to uniform electric field is always 0. But the net torque acting on the dipole, it may be 0, may not be 0. But net force is always 0 when the dipole placed in the uniform electric field. The case is uniform electric field. Okay. So now let me move on to discuss about the next concept, that is, up to here we have discussed about the discrete charge distribution. That means we have considered Q1, Q2, Q3, Q4 like this up to Qn like this. Now let us consider the continuous charge. In order to discuss the electric field due to continuous charge distribution, first we know to have some definitions, that is linear charge density. So the word itself says line, right? So what is the linear charge density? Here linear charge density is represented by the symbol lambda and it is defined as the linear charge density is the amount of charge acting per unit length. Okay, linear charge density is defined as the amount of charge acting per unit length, or charge per unit length is called as linear charge density, and it is given by an expression lambda is equal to, so delta Q, here charge is delta Q divided by delta L. Okay, this is the expression for the linear charge density, delta Q by delta L. And the SI unit of this linear charge density is, see, unit of charge is coulomb, unit of length is meter. So coulomb per meter. This is the linear charge density. In the same way, we have to know surface charge density. Surface charge density. The surface charge density is defined as the charge per unit area. Charge per unit area, that is called as a surface charge density, and this surface charge density is represented by the symbol sigma, and it is given by an expression, so that is delta Q divided by delta A or S. Okay, so expression for surface charge density is sigma is equal to delta Q by delta S, and its SI unit is coulomb per, area unit is meter square, so coulomb per meter square. And the third one is volume charge density. Third one is volume charge density. The volume charge density is defined as, it is represented by the symbol rho, and it is defined as charge per, so unit volume. Okay, so charge by volume. The surface, volume charge density is defined as the charge per unit volume, and it is given by rho is equal to delta Q by delta V, and its SI unit is coulomb per meter cube. This is the SI unit of the volume charge density. Now let me move on to discuss about the electric field due to the continuous charge distribution. So what is the expression for electric field due to continuous charge distribution? Okay, in order to find out the electric field due to continuous charge distribution, let us consider electric field due to continuous charge distribution. For that, let us consider the electric field according to Coulomb's law. Electric field due to the charge delta Q due to a small volume element. Let us consider a small volume element as delta V. Due to the small volume element and the charge in that small volume element as delta Q, what is the electric field? According to Coulomb's law, we can write the electric field due to the small volume element is also small, that is delta E is equal to 1 by 4 pi epsilon naught delta Q by R square. Okay. So now, according to volume charge distribution definition, we write, so the volume charge distribution or volume charge density is given by rho, that is equal to charge per unit volume, right, that is delta Q by delta V. So by this equation, we write the value of delta Q. So now take this delta V to this side, it will comes to the numerator. So in the LHS, so delta Q can be written as rho into delta V. Now substitute this value in this equation. So the electric field is given by delta E is equal to 1 by 4 pi epsilon naught into rho delta V divided by R square. This is the expression for electric field due to small volume element, that is delta. If we want to find out the electric field due to the entire volume V, we need to use the superposition principle. So according to the superposition principle, so here we have divided the whole volume into small volume elements, that is delta V, and we are finding the electric field due to that small element. Now in order to find out the total field due to the entire volume, we have to add up all these small electric fields due to small volume element. So according to superposition principle, the total electric field due to the entire volume, total electric field due to entire volume, I mean all volume elements, all delta V's for entire volume is given by E is equal to summation of the electric fields due to entire, so or individual small volume elements. So the summation of delta E for entire volume. Okay, so we can write E is equal to, if we take the summation, so here we can write so delta E value is 1 by 4 pi epsilon naught rho delta V by R square here. So 1 by 4 pi epsilon naught is constant. Now take that constant outside the summation. So we can write 1 by 4 pi epsilon naught. Summation of then remaining is rho delta V divided by R square for entire volume. Okay, this is the expression for electric field due to continuous charge distribution. So now from this we can conclude the electric field can be found, electric field at any point, or it can be found by using Coulomb's law and superposition principle for any distribution, either it is discrete charge distribution or continuous charge distribution or partly discrete or partly continuous charge distribution. For anything we can apply the Coulomb's law and superposition principle, and hence we can find out the electric field due to that. Okay, now let me move on to discuss about the next concept, that is Gauss law. Okay, so what does Gauss law states, and so expression for Gauss law. Let me move on to discuss about that. Here Gauss law states that the total electric, this is on the concept of electric flux. You already know about electric flux, right? So please remember that. So Gauss law can be stated as the total electric flux passing through any closed surface. Total electric flux passing or flows through any closed surface is always equal to Q by epsilon naught. Gauss law can be stated as total electric flux, so it is flowing through any closed surface is always equal to Q by epsilon naught. It means the total flux, if we consider any closed surface, so the total electric flux, that is phi, is always equal to 1 by epsilon naught times the net charge enclosed by that surface, if we consider this as a closed surface. So whatever may be the kind of charges. So here Q means, here in this Gauss law, Q means net charge. I mean the total charge enclosed by this closed surface. Okay. So we can also say Gauss law as the total electric flux that is passing through the closed surface is always equal to 1 by epsilon naught times the total charge enclosed by that surface. So and mathematically it can be written as phi is equal to Q by epsilon naught. Here Q is the total charge enclosed and epsilon naught is the permittivity of free space, and phi is the total electric flux. Now let me move on to deduce this Gauss law, I mean prove this Gauss law. So in examination they will ask you, so state and prove Gauss law. So now let me move on to prove the Gauss law. For that, let us consider a closed surface as a spherical closed surface. In that spherical closed surface, let us consider the closed surface is a sphere having the radius r. So closed surface is the sphere having the radius as r, and the sphere is enclosed the net charge as q. The charge enclosed by the sphere is q, and the total area of the sphere is S. In the case of sphere, the total area can be written as, it is nothing but in general 4 pi r square, right? So the total area of the sphere is 4 pi r square. Now, in order to apply the Gauss law, let us consider a small so area element. Now I have considered the small area element as the delta S. Now for the small area element, so I am drawing the normal. In the case of a sphere, normal should be always drawn along the direction of the radius. Normal should be always drawn along the radius of the sphere. Okay, this is the normal. And so the direction of electric field due to the charge enclosed by the sphere is, see here, so the direction of the electric field is vector E. Okay. Here normal and the direction of electric field are in the same direction. I mean vector delta S and vector E are acting both in the same direction. Okay. So now see, I mean due to this charge, here this is considered as a sphere. In that sphere, I have on the surface of the sphere I have considered a small. So see, this is a sphere. I have considered only small area element. From the center, it will be, the small area element will be in the shape of a cone, right? So, due to that charge enclosed by the sphere, the field is acting radially outward and the normal is also acting along the radius. That's why both are in the same direction. Now, we have to prove Gauss law. For that, let us consider Coulomb's law. According to Coulomb's law, we write the electric field due to the charge is given by E is equal to 1 by 4 pi epsilon naught. Electric field at this surface area due to this charge is given by 1 by 4 pi epsilon naught divided by into Q by R square, because from the surface to this point of charge the distance is nothing but the radius. That's why we have written 1 by 4 pi epsilon naught into Q by R square. From the concept of electric flux, the electric flux due to the small area element is given by delta phi is equal to E into delta S cos theta, right? But here the direction of electric field and the direction of area vector are same, right? So since both are in the same direction, angle theta is 0 degree, therefore cos 0 value will be equal to 1. So delta phi is equal to E into delta S, cos 0 value is 1. Okay. So now substitute the value of this E in this equation. So we get delta phi is equal to E means 1 by 4 pi epsilon naught into Q by R square into delta S. We need to find out this is the flux due to the small area element. We need to find out the flux due to the whole sphere. For that, the total flux is the sum of the flux due to all the individual small area element, that is summation of delta phi. Summation of delta phi means, so now 1 by 4 pi epsilon naught into Q by R square will be taken as outside the summation. So 1 by 4 pi epsilon naught Q by R square into summation of delta S. Summation of delta S means sum of the all small area elements, that is nothing but the total area, and the total area of the sphere is nothing but 4 pi R square. Now substitute this value in this equation, 1 by 4 pi epsilon naught Q by R square into summation delta S equation. So phi is equal to, we can write 1 by 4 pi epsilon naught Q by R square into summation delta S value is 4 pi R square. 4 pi R square. Okay. So now here this 4 pi, this 4 pi, this R square and this R square gets cancelled. Now phi is equal to Q by epsilon naught. This is nothing but the Gauss law, that is total flux passing through any closed surface is always equal to Q by epsilon naught. Or in another way, total flux passing through any closed surface is always equal to 1 by epsilon naught times the net charge enclosed by that surface. Okay. And then what is the significance of Gauss law? This Gauss law so can be applied for any closed surface. Not only the spherical surface, it can be applied for any closed surface. It may be of any size and any shape. That means Gauss law is independent of the type of the surface. It may be, so it should be closed surface, that's all, but it may be of any shape or any size. And the surface at which Gauss law can be applied will be called as the Gaussian surface. Means the surface that we choose for the application of Gauss law. Means if you consider this surface, and in this surface if we apply the Gauss law, then this surface only be called as the Gaussian surface, like that. So any surface at which Gauss law can be applied will be called as a Gaussian surface. And here charge means the total charge enclosed by that surface, means the sum of all the charges present in that closed surface. And this Gauss law depends on the inverse square dependence. This Gauss law depends on the inverse square, so dependence of the distance contained in the Coulomb's law. Okay. So this is about the Gauss law. In the next class, we will discuss about the applications of the Gauss law. There are 3 applications. I will continue in the next class. Thank you.